We'll give it another 30 seconds or a minute.
Okay.
All right, so let's begin. Hi, everyone. Welcome to the Polariton Chemistry webinar. My name is Matthew Dew, and I will be your host today. Before we begin, let me make a few announcements. So here's this upcoming schedule. So remember, each week, there will be a webinar every Wednesday at 9 a.m. Pacific time. And remember, you need to have registered at this link. And next week, we have Lagudakis. And for seminars in August and later, stay tuned. We'll send out the new schedule soon via email. Next, if you haven't done so already, join the Polariton Chemistry online community. This is a public Facebook group where you can post announcements about papers, job openings, etc., related to Polariton chemistry. We also have a YouTube channel where we'll post recordings of the webinars in case you missed it or want to rewatch them. Now let's discuss the mechanics of the webinar. So on the bottom of your screen, you have 3 buttons. During the talk, if you have any questions, click raise hand, and then at an appropriate time, I'll ask the speaker to pause, and I'll unmute you, and you can ask your question. If you have any questions, you can also type in the Q&A, and then those questions will be addressed at the end. And finally, if you have any comments or you want to have some discussion with fellow audience members, you can type it in the chat. Now, let me introduce today's speaker, Professor Todd Krauss from University of Rochester. Professor Krauss earned his PhD in applied physics at Cornell University. He studied under the guidance of Frank Wise, the nonlinear optical response of inorganic semiconductors and the vibrational properties of lead sulfide quantum dots. He then did his postdoc at Columbia University with Louis Bruce, contributing important work on measuring electrostatic properties of single quantum dots. In 2000, he began his independent career at University of Rochester, where he currently is professor of chemistry and optics. His group has diverse research interests ranging from the photophysics of single-walled carbon nanotubes to the use of quantum dots for biosensing and photocatalysis. Recently, his group began studying quantum dots in the context of polariton chemistry. Professor Krauss has won a number of research and teaching awards and is a fellow of the American Physical Society, Optical Society of America, and American Association for Advancement of Science. Without further ado, Professor Krauss, the stage is yours. You may now share your screen.
Okay, great. Thank you, Matt. It's nice to know that I'm still, even having been here for 20 years, still young enough that I get my advisors introduced in the bio. I don't know, at some point that will go away. Let me just full screen. Okay, I want to thank Hoel and Wave for the chance to present some of our new work. This is a new direction for us in taking colloidal nanoparticles into the polaritonic regime. And I really want to thank Matthew for frankly doing all the work to get this together today and putting up with my last minute things, my scatterbrain activities of late. So thanks, Matt, for that. So before, in case we run out of time, I want to acknowledge those who did the work. Really want to thank Frank Huo and Nick Vamavakis. So Frank's in chemistry at Rochester. Nick is over in the Optics Institute. And we're a nanoparticle spectroscopy group primarily. And so Frank has taught me a little bit about theory, enough, I wouldn't say I'm dangerous yet, but a little bit about kind of theory of cavity QED and materials. And Nick really is an expert in cavity fabrication, cavity QED, and polariton. So and I've learned a lot from them and from their students, Arkajit working with Frank and Lang Yu working with Nick. And so in the work you'll see today, Lang Yu designed the cavities, made the actual cavities themselves, and then took the angle resolved measurements. Arkajit did all the theory. And then from our group, we made the nanoplatelets. That was Willie, who's here in the blue, and Mahilet, who wasn't in this group meeting, so she's cut out of the Zoom. We'll get a picture of her soon. And then Ovishek, who did all the spectroscopy on the platelets. All right, so I want to just introduce a little bit cadsalon nanoplatelets and their kind of photophysics. They're not that common in nanomaterial, much less common than their cousins, the spherical quantum dots. So I want to give everyone at least a sense of what their electronic and optical properties look like, primarily to motivate why of all kind of things nano that we chose the platelets to look at for forming these polaritons. And then most of the talk, the meat of it will be spent on presenting really properties of cadselenite exciton, nanoplatelet exciton polaritons. And we chose a dielectric cavity, and I'll explain why and say a little bit about the trials and tribulations in getting that to work, showing you some reflectance, photoluminescence measurements, and then some great simulations from the Hua group. And then if we have time, maybe a quick applications. We have a long history of photochemistry in our group. And so naturally we were attracted when polariton chemistry started to gain traction a few years ago, right? And so maybe how we could contribute in that area. Okay, so cadsalon nanoplatelets are a colloidal nanoparticle, similar to, like I said before, to quantum dots. They've been around for about a decade in research. The way they're made is similar to the way you would make a quantum dot. So you put, there's some notable differences. You would put the selenium, instead of injecting it with as a solution, you just put the selenium powder right in to octadecene solution, you add cadmium oleate, and then you add the acetate of cadmium. And that cadmium acetate is what really triggers the platelet formation. You end up with these kind of napkin-looking things. They are 10, as you'll see from the TEM, 10 or so nanometers on a side to 20. That can be controlled. The thickness, though, can be precisely controlled to within a few monolayers. And you can change the thickness by changing temperature, or you can also change the thickness by workup, so that the different thicknesses have different buoyancies, essentially, in the organic solution. And you can centrifuge them out, for example. And that does a pretty good job at separating different thickness platelets. They are highly crystalline, and this is really, the thickness is a really important issue, which will manifest itself in the optical properties. But unlike quantum dots that have a distribution in their size, right, which you can't really get away from, it's very challenging to get less than even 5% size distribution. Platelets can be essentially exact, right? And this leads to very nice spectra, as you'll see in a few minutes. The platelets are hydrophobic. They're covered in oleic acid, as I tried to indicate here with the squiggly lines. This is convenient, right? It allows you to work with platelets in organic solutions, and as you'll see, they're very useful for depositing them inside of cavities. So on the top is just a cartoon of what these platelets look like. We call them 0.5 extra monolayer, right? So 3.5 monolayers or 4.5 monolayers. And the reason is that they're coated by cadmium, terminated by cadmium on the top and bottom, okay, in the transverse direction. So give you an idea of their size, a 3.5 monolayer platelet is roughly a nanometer and a quarter thick. So the platelets we're working with are primarily 4.5 monolayers. So they're going to be slightly larger than this, about a nanometer and a half, right? And so the ones we use for this study are kind of like napkins. Like I said, they're square, about a little less than 20 nanometers on a side. If you're lucky in the TEM, you can get a nice cross-sectional view, a nice side view, where you can see the thickness of the platelets directly. And so, for example, here, if you have a decent monitor, right, with good resolution, a 4K monitor, maybe you can see the columns of atoms there, platelets giving the exact thickness. Now, how do we understand platelet electronic states? Well, the simplest kind of model is a two-band effective mass model, which, in your undergraduate quantum mechanics class, you call a particle in a box, right? And so a particle, kind of a quantum well, particle in a box works pretty well to get the basic photophysics of the platelets. But as you can see here, right? So what you do is you take in the particle in a box model on the left, you have your conduction band and your valence band, and you simply just quantize that with allowed energy states of the cavity, allowed wave vector states as shown here. But this really isn't a good approximation for platelets, right? Primarily because, underlying this conduction band it's really derived from the interaction of cadmium 5s orbitals, whereas this valence band comes from 4p orbitals, right? And so, way back in general chemistry now, some time ago, right, you learned that p states, there's 3 px, py, and pz orbitals. So that really should lend itself to 3 bands. And that's what you see in the bulk band structure of cadmium selenide. So on the right here is a more accurate representation. This is from Sasha Efros's calculation from a paper with Benoit Duboutre back when 10 years ago, roughly. And you can use various levels of theory, but the basic idea is if you include now this conduction band and then all 3 valence bands, so they're not labeled px, py, pz, they're labeled heavy hole, light hole, and then a split off band. Then you can get the platelet photophysics pretty accurately, right? So now as you take this band structure and you confine it, right? You introduce discrete states in wave vector in K, and then you can see clearly that, as you make the platelets thinner, you start to make the platelet electronic band gap bluer, right? That's not unexpected, but also you see the energetic distance between the heavy hole and the light hole bands gets larger, as well as between the split off band, but generally we don't see this, it's so far away spectrally. These two you can see quite clearly in absorption spectra, as you'll see in a second. So unlike the spherical quantum dots that have continuous distribution of sizes, right? So you can get a continuous color distribution here, you get discrete colors for the platelets, right? And so for example, in jumping from a 3.5 monolayer to a 4.5 monolayer platelet, you get photoluminescence kind of in the blue and then in the kind of blue-green, nothing in between, right? There are no other colors you can access. And you can see that here in this paper from the Muril's group, like as you change the thickness, the photoluminescence jumps in these discrete colors. You can see quite clearly the heavy hole and light hole for both the 3 monolayer and 4 monolayer platelets. And the reason why they're so distinct, right, is again because this thickness is really uniform, right? And so, again, unlike the quantum dots, you really only have one thickness. Thickness determines the energy of the band gap, and so therefore you get very narrow resonances, right? You don't get that large inhomogeneous distribution. In fact, this is really borne out in single particle studies. So, we've done some single molecule photoluminescence on just the bare nanoplatelets, and you can see that that's the noisy spectrum here in the blue. The full width half max of the photoluminescence, this is a little bit larger platelet, a little bit thicker platelet. But even for this thicker platelet, right, there was hardly any variation in the inhomogeneous distribution compared to the ensemble, which is in red. So why is this important, right? Why is this relevant here? Well, we were looking for strong coupling, and evidence of strong coupling, as everyone very well knows, is to see Rabi splitting, right? So again, calling upon classic quantum optics for an atom, right? When you couple an atom to the cavity, you get this Rabi splitting, and therefore in your absorption electronic spectra goes from a single state to this, upper and lower polariton state. So if you have narrow photoluminescence spectra, which you get for the platelets, then we thought it would just be easier to see in transmission or reflection, some kind of absorption measurement or proxy for absorption, to see these 2 peaks, see the 2 branches of upper and lower polariton. And we think that actually is the case, right? As you'll see in a few minutes. But also, we had other reasons for choosing platelets. They just have huge oscillator strengths, right? So we're pretty familiar with the quantum dots versus dyes. Let's say a dye molecule or some metallic like a rubipi. They have much smaller oscillator strengths by a factor of up to 10 compared to quantum dots, right? And now the platelets being larger, if you have those collective oscillations in the plane, you can get even larger transition dipoles than the dots. So we thought that having a large oscillator strength of the platelets would be really advantageous because, as probably many know on the call, the oscillator strength determines the coupling, which then determines the Rabi splitting, which again determines your ability to see, determine anything if you have some coupling, right? Also, the alignment of the electric field with the transition dipole is important, right? For molecules that are one-dimensional in nature, it's quite possible that you just misalign things to the point where you don't have very strong coupling. Quantum dots are the best. They're spherical. They have effective three-dimensional transition dipoles, but platelets are two-dimensional. And there are well-known techniques for aligning platelets, essentially in the plane of the electric field, right? And so therefore, we thought that would be another advantage of platelets, having a strong two-dimensional transition dipole. Now, finally, we were noticing this nice paper by Matt Safer recently that came out in ACS Photonics, where they were arguing a couple of criteria are important for looking at applications that, again, many people on the call are probably familiar with, singlet fission or charge transfer, energy transfer inside of a cavity, and seeing if the polariton could modify some of those properties. They argue that not only do you want strong coupling, but you also need long photoluminescence lifetimes if you want to see some of these effects. And generally speaking, nanoparticles have longer photoluminescence lifetimes than dye molecules by factors of 3, 4, or 5 or more. As an example here, I take this from Benoit Duboutré's paper on kind of single platelet photoluminescence dynamics, and they're getting most of the lifetime is in a 16 nanosecond decay, which is roughly 4 or 5 times longer than, let's say, a dye molecule. So all of these together suggest that platelets would be a good idea to put into a cavity to look for strong coupling if you're going to use a colloidal particle. And it surprised us when we started this that there isn't a whole lot of work out there on using colloidal particles for coupling to cavities. There's plenty of work on kind of self-assembled quantum dots, right? These are ones made by CBD, but not the chemistry ones, not the colloidal ones. There are a few, and so this paper came out a few years ago. Quite interesting paper where they put platelets onto one mirror, forming a Fabry-Perot cavity. The other mirror was actually effectively on a translation stage, and by translating the mirror, one can change the cavity tuning, which I thought was a very clever way of doing it. They did get evidence of strong coupling through absorption with a 60 millivolt Rabi splitting. But we didn't want to pursue this, and work off of this because it just seemed really hard, right? I mean, it was very challenging to get that mirror to move and have a good cavity, and it seemed very difficult if one wanted to do scale up, right? So one thing in the back of our minds is, hopefully we'll get to at the end, is doing chemistry, right, with polaritons, as many here is the purpose of the webinar. And if one's going to do that in a massively parallel way, it seemed difficult to do that using this approach. Be a more facile approach with respect to chemistry would be to use plasmonic cavities. So here's an example of one. It's just a nano thin film of gold where they put the platelets on top, came in on the backside through kind of this total internal reflection geometry to excite the platelets. This worked. They got reported a Rabi splitting from a couple of years ago now in 50 millivolts through a reflectance measurement. We saw that this particular metal cavity design was challenging just to get high Q factor, right? The metals are just lossy, and so it would be difficult to really get high Q being quality factor using this type of cavities. One way to get a high Q, though, is to make a lattice, right? And then start to get some interference, and Dave Norris's group did that. And so this is some work from David's lab, and he published a paper a couple of years ago describing how you could make a silver film, punch some holes in it with a well-patterned array, and then you get these whole array cavities. David's lab got great Rabi splitting, right? Really, relatively speaking, pretty strong, 150 MeV, and it was measured through photoluminescence and reflectance. Again, with the metals, it was pretty hard to get high Q factor cavities. In fact, in this paper, there was a line where they claimed to have saturated the light matter coupling strength, right? So we decided to go in a different direction, one that has potential to get really high Q cavities, which meaning really potentially ultra strong coupling, right? If one could get there. We didn't think metals would, at least in this configuration, would do it. We settled on trying to look after dielectric cavities, which has its own problems, as you'll see, right? And so we made a Fabry-Perot cavity. One mirror was a distributed Bragg reflector, dielectric mirror, and it was made by taking alternating layers of silica and silicon nitride, right? 10 pairs. And then on top of that, we put the nanoplatelets in polymethyl methacrylate. I'll describe that process in a minute. And then we put a silver mirror on top with a variable thickness, right? So we had to kind of Goldilocks the silver mirror. If you made the silver mirror too thin, then the cavity was too lossy, right? If you made it too thick, then you had a higher Q cavity, but then you couldn't see any photoluminescence, coming out vertically out of the cavity. So we had to kind of choose something in between. Then we capped it with some silica just for protection from the environment, right? So it took us a while to get, this is a lot of things in research, right? It's the little things that really hold you up. So it took a while to get this middle layer, this PMMA nanoplatelet layer to actually be well behaved, right? So because spinning PMMA has been done for decades, it's well understood, it's very easy. You get, as you can see here from this optical image, like beautiful films, right? Beautiful thin films. When you add the nanoplatelets, because they're coated in these alkanes that don't quite mix well with the PMMA, you get aggregation if you're not careful, and then you get the films that look like this, which we would describe as bad, right? And those are lossy and don't lead to strong coupling. Overcheck worked pretty hard to get films that were well behaved and had good optical quality. And so there's a prep for this that took them some time to work out. And then once we had that, then we could move on and start to make cavities. Now, Langyu was really calculating the thickness of the cavity, to get the resonance of the cavity and the platelets exactly on top of each other. And one of the disadvantages of having a narrow resonance in your matter properties, right, is that you have to be much more fine in hitting that resonance with your cavity. And so it took, again, Overcheck some time to figure out how to, basically get this simple stuff, like how one mixes PMMA and platelets in the right solvent and spins everything out to get the right thickness we need, which is roughly 173 nanometers. So, we're stuck here somewhere on this curve, right? So once you figured all this out, then you could go ahead and make cavities. So remind you, on the left are the 4.5 monolayer platelets that we're using. They have a photoluminescence peak around a 2.43 EV. On the right is the reflectance of the cavities that Langyu made. Cavity quality factor was not bad, right? It's 270. You can do better, again, if you were a bit smarter about the mirror. But in this case, we opted for simplicity rather than the perfect cavity, right? And so now we need to characterize the cavity properties as a function of in-plane wave vector, in-plane momentum. And for that, we use a Fourier-based spectroscopy system, which is, an optics faculty member's way of saying a microscope, right? So just use a microscope. So a microscope has this objective that's used to focus in the excitation light on the sample. It's an infinity corrected objective, so it collects the fluorescence or reflectance from the sample and sends it, an image at infinity. You have to kind of focus that image down, and the way you do that is with a tube lens. So you project that image now onto the slit of your spectrometer, and in this way, you can use angle information, which, as you'll see in a second, maps onto in-plane momentum, in-plane wave vector. You can easily map that onto your CCD camera. Okay. Okay, so here's the cavity again, and this is what the cavity resonance looked like as a function of angle, right, in reflectance. And so these are standard equations, right, for what in a Fabry-Perot cavity, what the energy of the cavity mode should look like as a function of in-plane and out-of-plane momentum. It's just the square root of the sum of the squares, right? And then by making the substitution here for tangent of theta is the ratio of the in-plane over out-of-plane momentum, you can get an expression for what the energy should look like as a function of angle, right? And so the red dotted line there is just a transfer matrix simulation of what the cavity energy should look like. And not surprisingly, the cavity behaves as expected, right, for these low incident angles. Okay, so earlier we discussed, quantum optics of atoms, right? Where you get these upper and lower polaritons formed, as well known to this group, right? From the hybridization of the ground state with one photon and the excited atom with no photons in the cavity. I just stole this graph. I tell my students sometimes it's better to steal than invent, because Hoel in his paper has a great graph describing what the dispersion should look like for in-plane wave vector for a matter polariton, an exciton polariton, right? Now, an exciton in a semiconductor does have a dispersion itself, right, that varies with wave vector, but on this scale, because the electron is so much heavier than the photon, essentially, right, the photon has effectively no momentum, and then you get the exciton is actually flat. And so, when you get this crossing, this resonance here at a certain angle, or at a certain wave vector, then you get an anti-crossing, or as Roald Hoffman used to say in class, the bands are repelling, right? So that's the signature of the polariton formation, is the bands repelling. And again, the coupling strength, how well your cavity couples is dependent on how much those bands repel, or, is given by the Rabi split. Okay, this should be well known. So what's the data we get, right? So on the left is the reflectance data, and on the right is photoluminescence as a function of incoming angle, which again is as a function of in-plane momentum. On the left, you see in the reflectivity, you see two branches clearly, right? You see the upper polariton branch in quite strong reflectance, especially at these high angles, and then you see the lower polariton branch here. Photoluminescence, you don't really see evidence of two branches. We just see what looks like a lot of photoluminescence clustered at one angle in the lower polariton branch. So we want to understand this, right? We want to understand why is the, fundamentally, like what's causing the photoluminescence to be only from the lower polariton? What's causing it to be at such high angle and not anywhere else? And then why is the reflectance, generally speaking, strongest from the upper polariton branch, and why is it only at high angle? So for that, we have to turn to theory, right? And so again, I ripped off this figure from the same paper from Hoel. So we have this, Frank is teaching me about all these Cummings models, right? The three Cummings models, as we know from theory. So there's the James Cummings model, right, which is the simplest model of one atom coupled to the cavity. If you have n-like emitters, then you get the Tavis-Cummings model. The main feature there is that you have this collective state coupled to the cavity, and then everything else is this other mass of dark states. Dark, now, I always get to be clear on this. Dark does not mean optically dark in free space, right? It means uncoupled to the cavity. I'll stick with the polariton terminology, but there are also dark states in the platelets that are truly dark, as in not coupling to light at all, right? So what Arkadjic used for this work in trying to model the cavity was a Holstein-Tavis-Cummings model, which is taking that a bit further and including the effect of phonon. So there's 4 independent terms in the Hamiltonian. Now, for the theorists, sorry to disappoint, but I will not be showing many details of the Hamiltonian. Okay, please look at the paper if you want to see all the gory matrix elements that Arkadjic came up with. But the basics is that there are 4 terms. There's a platelet term, which consists of n independent nanoplatelets. And we'll describe what that is in a second. There's a mode that describes the cavity mode. There's a term Hamiltonian that describes the interaction between the cavity and the platelets. And then there's this Hamiltonian that describes the photoexcitation of the platelet. So the platelets are modeled with a 3-level model. There's a ground state, and then we use a classical electric field to excite, in the CW laser, right, to excite the platelets to an excited state. And then that excited state, which it's only one state in the model, it represents the entire continuum of platelet excited states. The excited state decays very quickly. In experiments, this is sub-picosecond, fraction of a picosecond, non-radiatively back down to the heavy hole. And then that's where it sits before, in free space, it would radiate. Right? So the light hole state is not included in the model. Okay, we don't see it in the spectra, as you saw before, so we didn't include it. But it does include a model, a detailed model for exciton phonon couplings, which will be important. And again, if you look in this reference, if you want all the gory details on the exciton phonon coupling. Okay, the cavity is modeled standard, n plus H bar, ladder of eigenvalues, right? And so you have these creation annihilation operators. And again, you have the angular dependence of the energy. And then I did not include the interaction Hamiltonian and all the complicated terms, but the essential physics is captured here in this light matter coupling strength, right? Which is proportional to the oscillator strength, right? Proportional to the transition dipole, proportional to this dot with the electric fields. You have to have it aligned properly, right? But the stronger the oscillator strength in your matter, right, the stronger the coupling, which again is why we chose the platelets. It's also inversely proportional to mode volume. It's another reason why we chose a dielectric cavity is that we felt like, although our Fabry-Perot cavity isn't ideal for this, there are lots of opportunities based off of this to make cavities with smaller mode volumes. So from experiment, you can back out what the coupling is, and then that allows you to get the number of, just an estimate of the number of platelets coupled to the cavity. It's around 1,400, right? Now, Arkajit wanted to graduate sometime this decade, right? So he didn't want to run a calculation with 1,400 platelets in it. So as is common, he cut that down considerably to about 30 platelets. We know the laser energy. We could get the laser coupling strength, right? Those are parameters we put into the model, and then you could turn the crank on the calculation. Okay, so again, there are expressions in the paper for the energies of the upper polariton, lower polariton, and their eigenstates.
Professor?
Okay, so here's what?
Oh, we have a question from the audience.
Okay.
Okay.
Oh, hi, Todd. I have a question. I mean, this number, okay, can you just go back to the previous slide? I mean, this number n is often not easy to obtain experimentally. How do you get that? Because both G sub C and n are not necessarily the easiest things to obtain. So can you elaborate on how you're obtaining those numbers?
Yeah, so I have to go back to, there's a whole description actually in the paper, which I don't know if it makes sense to go through it here.
Okay.
But effectively, it's gotten from the Rabi splitting, okay? And,
sure, but I mean,
I agree, and we say it's an estimate, okay? It's an estimate. It is not, we're not saying it's exactly 1391 or something like that.
Okay, yeah, because I mean, the square root of n times G obviously is easy to get, but then each of them is not necessarily easy. And I think sometimes those numbers n matter a lot in dynamics. So that's why.
I mean, we have estimates for the mode volume. We have estimates for the, for what the transition dipole is. And so all those numbers are known. So one has, one can get a ballpark GC from that,
Okay.
It's not, again, I wouldn't say it's 2%. No, don't put 1% error bars on that. But order of magnitude, I think it's pretty good.
Okay. And maybe this is another question related to your first part of your talk. Maybe it's a bit stupid, but I still ask it. So, so you're saying, okay, nanoplatelets have a much larger transition dipole than molecules, but then you also say the lifetime, the PL lifetime is much longer. But then is this just because the non-radiative decay is much smaller for the nanoplatelets?
Yeah, so their photophysics is in some level similar to dots in that they have a longer lifetime because there is a dark state, right? There's a state that is forbidden, optically forbidden, that sits below it, and there's some dark bright mixing of that into the state. So that does change the lifetime and make it longer.
Okay, but then the absorption itself is brighter because the dipole of the bright state is much larger than than a regular organic dye, for example. Is that, am I understanding correctly? Okay, thank you.
All right, we have one more question.
Okay.
Hello, can you hear me?
Yep.
So I mean, I have a question exactly on this thing. So I mean, a very basic question. So what is the fundamental difference between this photoluminescence and reflectance? I mean, I'm not familiar with this.
So I guess you kind of broke up on my end. The fundamental difference between the photoluminescence and the reflectance.
Yeah.
Is that in the cavity or with just the platelets in free space?
I see. Okay. Mm-hmm.
So I don't fully understand. Are you asking about the polariton or just the free space exciton?
No, I'm just asking like I mean like the information that the reflectance gives, reflectance spectra gives versus the information that photoluminescence spectra gives.
I see. Yeah. So I mean here the reflectance is giving you information that is can be related to absorption essentially, right?
I see. Okay.
Yeah. Whereas the photoluminescence is emission, and those are different in so much as photoluminescence comes from the in free space, right? The excitons that have decayed all the way down to the heavy hole state, right? And so in free space, there's this continuum of energy levels in the platelet that allows for very efficient non-radiative relaxation. It's different than molecules in that way, right? And whereas you can get non-radiative relaxation within a fraction of a picosecond. And so, we would expect to see, well, we didn't know what to expect to see in polariton, but traditionally most groups that report on polaritons have seen similar thing, right? Where they see only photoluminescence from the kind of the lowest energy feature, that's very common because of the quick relaxation, right? Whereas in absorption, you can get all allowed transitions, in principle modulated by Fermi's golden rule, right? Density of states. And so one would expect to see in reflectance, kind of the allowed transitions of the upper and lower polariton, as well as higher states if we had scanned that far. Does that help answer your question?
Okay. Yeah, that perfect answers. Okay, thank you.
Okay. Thank you. Thanks for the questions. So the red lines here are the theoretical fits. From that, you can back out the Rabi splitting at 0 detuning, right? You can also back out the detuning. The detuning simply is the difference in energy between I like to think of it as the difference between the polariton or the cavity mode resonance with nothing in it, and then the exciton photoluminescence in free space, and that's about 130 MeV. So it's quite a lot of detuning. I really like this figure because it shows that ArchiGit really has the theory working pretty well, and we're getting not just qualitative agreement, but really quantitative agreement here, right? So the white dashed lines are again these upper and lower polariton energies, and this is the theoretical model. But what then ArchiGit went through and modeled the actual photoluminescence signal and captured not only the fact that the photoluminescence should be in large angles, but also quantitatively the asymmetric upper polariton and lower polariton intensities, right? And we'll get into why that is in a second. Naturally, as you start making cavities, you don't make them all the same. At least we would love to make them all the same, but we can't. Experimentally, they're all different. And so, for example, we made 3 cavities with roughly the same Rabi splitting, right? But different detuning. So one was a pretty small detuning, one was larger, and then one was larger still. And so from the photoluminescence kind of dispersion maps as a function of this axis will show up in a minute. It's again in plane momentum. You can see that for the smallest detunings, you're getting kind of the full lower polariton branch emissive, right? But as you start increasing the detuning, it concentrates at these high angles. So ArchiGit went and modeled that, and again, seems to get it pretty quantitative and model as you start increasing the detuning, the photoluminescence clusters out at these high angles. So now, what physical insight do we have provided by the theory, right? And that's something that I think was really nice, in that we were able to get some understanding of what fundamentally goes into these plots. So we go back to the original figure, right? And so ArchiGit is trying to model both the small angle and the large angle data here, right? And so these 2 figures just show you what the energy state should look like in a Travis-Cummings model with no phonon fluctuations, right? Where these dark states are sitting here fixed. In reality, if they have phonons coupling, then these are going to fluctuate energetically and dynamically, right? And so then he calculates what I call these, I call them spaghetti plots, right? So these are trajectories, including the phonon coupling. And you see, I want to highlight a couple things. One is for small angles, right, the lower polariton, even though it has all of the photonic character, is really detuned from this exciton dark state manifold, right? Contrast that with the large angle where you're in resonance. Now the upper and polariton branches have significant photonic character, and as well as these dark states. You see quite a lot of photonic character if you look at the spaghetti, kind of mixed into these dark states. And so the phonons, in kind of theory speak from Frank, right? The phonons are mediating transfer between upper polariton and lower polariton branches through the dark states. I like to think of it as just you're brightening some of these dark states through phonon coupling.
Professor?
Then, yes.
I have a question. So do you include in the model the dark states, not the dark states shown here, but I'm talking about the dark states of the quantum dots, because I imagine that, there are phonons that can couple, right? The dark states of the quantum dots to the bright states of the quantum dots.
Yeah, so that's a good question. In this model, it is not included, right? But it is an important aspect of the photophysics that couples the non-radiative dark state to the bright state, which then should be coupled to the cavity, right, in some way. So we have not included that here. Just a simple three-state model. That's on, one of the list of things to do, actually, is to make a more accurate platelet model.
But I guess, are you able to capture qualitatively all the main features without including those dark states?
We think so, yeah.
Okay. So why do you think that the non-radiative processes that couple the the platelet dark state to the platelet bright state? So why do you think that is not important here?
So that's a good question. I mean, it may be that coupling is just not really strong. Although, it's interesting because we'll have to think about it more, Matt. At low temperature, you do see the effects, which is where all this data was taken, right? You do see the effects of the dark state more because the dark state's only a few MeV below this bright state. And so at room temperature, it's generally populated. The bright state's populated, right? But at low temperatures, it's not. And so that is a good question to think about that, right? I have to think about that. I mean, maybe this is something that we could put into the model, add a fourth state in there and see how the effects are. No, that's a good question.
Okay, thank you so much.
It's just too, it doesn't have enough oscillator strength to really make a difference, but I don't know. Okay, and then Arkajit ran some quantum dynamics simulations.
Oh, Professor, sorry. Yeah, there's actually one more question.
Okay, go ahead, shoot.
So, okay. No, from the audience. So, okay. Aaron, you may ask.
Okay. Hi, Todd. This is a really nice talk. And it's a lot of really interesting results. I think one thing that, the mediation of non-radiative relaxation between the polaritons and dark states has been seen in several other kinds of polaritonic samples. And it's often argued that these vibrations, or in your case, the phonons, mediate resonances between them. What are the phonon frequencies for these? I imagine they're fairly low, like a couple hundred wave numbers. Is that correct? That's correct. Yeah.
I mean, it would be the optical phonon of cat selenide is on the order of a couple hundred wave numbers.
So then essentially that's about half of the Rabi splitting that you guys are observing, right? Which is on the order of like 55, 60, 65 MeV.
That's right.
Okay. All right. I wanted to remind myself of all that just to make sense of it. Thanks a lot.
Yeah, sure. No, that's a good point. I mean, these are pretty heavy atoms, right? Okay.
Right, you may continue.
Okay, thank you. So, the dynamics were calculated. Again, I don't want to skip some of the details of actually how that was done, but just focus on the results where Arkajit shows here for both the low angle and high angle detunings, the ground state, right, which is immediately depleted by the laser, the dark state, which then all of that population ends up in that exciton largely, right, grows and then reaches a steady state. The hot exciton state, that is in the yellow here, which just has a brief existence and then decays quickly. And then you have the upper and lower polariton populations, which again, even though the upper polariton is populated here, doesn't have much photonic character at the zero detuning, whereas when you're in resonance, the inverse is true. Okay, so finally, we don't entirely understand this, but we do have some data at room temperature. As you start to increase the temperature, the Rabi splitting, at least is what we measure, drops. We're getting some additional coupling that's not, not from our polariton, not from our nanoplatelet, right, showing up here, but basically looking at through the modeling, we're getting some strong coupling at room temperature, which is exciting, right? Because that really ties into this idea that has been really heavily talked about in this polaritonic photochemistry. So I stole this slide from Archigit, and it's getting late, so I'll just list all of, this got our attention, and we've been following this from kind of the outside a little bit, but there's so much beautiful work, largely theoretical, but some experimental in trying to use a cavity to modify chemistry, right? And we've been thinking about photochemistry in free space or in solution really for some time, right? And nanocrystals really have an advantage there, we think, over things like rubipi or iridium complexes or organic dyes for several reasons, right? One is just a practical reason, is that the nanocrystals are just robust. They're little rocks, right? And so this allows you to get a lot more chemistry done before you have a catastrophic event to your particle, right? Also, and this is really a fundamental advantage, which is we're discovering more and more important. You can tune the redox properties of the nanocrystal with size, which means that you have independent control over your surface chemistry and electronics, right? If you have this iridium complex and you want to change the energy at which an iridium delivers an electron, you got to change what the iridium is bound to, which is not only, involves some chemistry, but also could, is a coupled problem, right? Here, you want to change the energetics of the electron or the hole, you just change the color of the nanocrystal, change the size, and the chemistry can be the same, right? So for all these reasons, we've been having some effort looking at photochemical hydrogen production, right? And so, and this has been going on for some time. This original paper was just a collaboration with Rich Eisenberg and Pat Holland while Pat was here. And so using, transition metal catalyst, in this case, it's a nickel dihydrolipoic acid catalyst, we can produce hydrogen from protons with, this is an obscenely long experiment on our timescales, it's like weeks this thing runs, and it's very robust and it's very active, and it has, million turnovers and high efficiency, right? So already the system's pretty good. But we were interested in trying to understand why this works so well. And so we spent a lot of time looking at dynamics of the charge transfer. So I'll give you a snippet of that, right? And so, for example, if you do transient absorption spectroscopy and you excite high up in the energy bands, electrons quickly decay. These are for nanocrystals now, spherical particles, back down to this lowest exciton state under a picosecond. And then you sit there and watch how long they're there without any catalyst, without any electron acceptor, they last nanoseconds. Okay? But if you add the electron acceptor, then you have a quick, on average picosecond, tens of picosecond decay, right? And the reason why this is so fast, we're still trying to understand, but the bottom line is that this transfer rate depends on the amplitude of the wave function at the surface of our quantum dot, right? That's really so it would be this H squared term, this matrix element in the Marcus model. And so platelets having a wave function that is almost all surface, right? Much higher surface charge density. We thought they would be really good for this application. And so it got us thinking about platelets and cavities. We also are thinking about organic chemistry. We have a collaboration with Dan Weitz, who's at Wisconsin, using nanocrystals to make new bonds. And I'm gonna skip some of the details, especially here, but in this one kind of typical photoredox catalytic reaction, nanocrystals are orders of magnitude better than iridium dyes. They have tens of thousands of turnovers. We reported this a few years ago, and Emily Weiss at Northwestern reported on nanocrystals for photoredox catalysis. She has a number of nice, interesting papers in this area. So again, this got us thinking about maybe this could be something that could intersect with the cavities. And the bottom line is that charge transfer is often the first step in either a fuel forming reaction or in a photoredox reaction, right? And so this tied into some work that really what I'll describe briefly is an experimentalist take on Archegit and Frank's work here. And so thinking about if you put nanoparticles inside of a cavity, right? Can the electron transfer rate be tuned, right? I know many others, perhaps some on the call, are also thinking about this as well. And so, Archegit was testing various levels of theory here. Janus Cummings, rotating wave approximation, perturbation theory, the exact solution where possible, and then this Pauli-Fierce model. And then this is the model system that was used, right? So it's a pretty simple system where the nanocrystal, again, is just divided up into a ground state, an excited state, and then there's an acceptor state that's not coupled to the cavity, right? And the details, again, if you want to see all the gory theory details, it's in here. But let me tell you what excites me about this. So the cavity can control charge transfer, and I see this figure on the right, and I'm thinking, possibly we could get at this experimentally, right? Because for reasonable coupling strengths, a couple hundred MeV, and a driving force that we can access easily with our, for example, our nickel catalyst and the cad-selenide system, we should be able to enhance the, potentially enhance by an order of magnitude, the charge transfer rate. Or we could suppress it, actually, by an order of magnitude. And we have a lot of headspace to suppress that rate, right? Since the charge transfer is so fast. So the challenge is if you want to enhance the rate, you may have to look, and what this is telling me is you may have to go from the upper polariton to do it. And that may not be so trivial. Now you can also look at, for a zero free energy difference in donor and acceptor, right? You can look at how the varying the coupling changes the rate. And again, what's tantalizing is you can change it by several orders of magnitude. It's a pretty strong dependence. So can we actually get to these coupling strengths? It's not clear, right? There's a route to it with other cavities, maybe not the Fabry-Perot cavity, but if you could, then that could be really exciting, right? Because since again, your efficiency of catalysis depends on that electron transfer directly. And finally, I like this figure from Archegit where, again, for zero free energy difference donor and acceptor, Archegit varied the coupling strength and the detuning. And what's exciting is that, again, you're getting a significant change in the rate. In fact, you could potentially drive energy transfers uphill from the upper polariton, which is interesting. But practically speaking, we're pretty close, right? We're pretty close to the parameters, detunings on the order of 100 to 200 MeV and coupling strengths on the order of 100 MeV, where we can kind of hit some of these theoretical predictions and maybe see a change in the rate. So we're excited to start doing that. Okay, so let me conclude. So we think that nanoplatelets in dielectric cavities are a promising quantum system. These colloidal systems, they do have strong coupling. They do show strong coupling at room temperature. You can see that in, as we discussed, the reflectance of photoluminescence. Archegit and Frank Huo have put a theoretical model on this that allows us to understand some of the photophysics as a function of detuning, understand the population dynamics. But this is only one paper. Where are we going with all this, right? And so we have some new directions in understanding exciton polariton lifetime, right? So there's this discussion is whether the polariton lifetime is really dominated by the cavity lifetime or dominated by all these coupling to all these dark states and the exciton lifetime. So we're interested in looking at that. We're definitely looking at new cavities, trying to, and the dielectric cavities have promised to localize the mode volume. The challenge there is to put the antinode of the field where the nanoplatelets are. And then, as we discussed in some of the questions, as an experimentalist, it would be great if we could get more accurate representation of the platelets, including those intrinsic, free space dark states, as well as the other excited states like the light hole as well. I'll just leave you with one thing. So we're, as an example of new cavities, we're collaborating with Terry Odom. She has these beautiful metal lattice plasmon cavities. Now they're different from holes in that they still have a resonance because of the lattice, right? But now you have these these metal bumps that localize the field in particular ways, and also they really are facile for doing chemistry, right? Because you can flow solutions in these things pretty easily. So Terry's cavities have resonances in the visible, and this is some recent unpublished data where we're starting to see some repelling of the bands, indicating coupling to these cavities with the platelets. All right, I think I'll stop here and leave you with a couple pictures of the Rochester campus during the day and at night. And I'll say thanks again for everybody for being on the call, whether you're in the afternoon, morning, or evening. And thanks again for the invitation, and happy to take any final questions.
All right, thank you so much, Professor, for a very nice talk. Now let's get to some questions. So how about we get to the Q&A questions? Professor, do you see some of the questions in the Q&A?
I can click on it. Okay.
Yeah, so we have questions from Caleb and Madeline. So we can get to Caleb's question. I believe everyone can see the Q&A questions in their chat. So go ahead, Professor.
Thanks, Caleb. Thanks for coming on. Caleb's a U of R alum, so this is home cooking. So I guess it's a question, Caleb has a question about loss in the metals. And so would the conductive oxide or something like that have as much loss? And so it's a good question. I don't think those conductive oxides have very strong plasmonic effects, because their density of states isn't the same as a metal, right? And they also their dielectric properties. Silver is great because it has this negative dielectric constant in the visible that gives you the really sharp plasmon resonance. So I'm not sure, Caleb, that those would be ideal. We're moving towards dielectric cavities and using lithography, essentially, right? Using lithographic techniques to pattern cavities that are, again, and using nanofab, just like the Fabry-Perot cavities, to make smaller mode volumes with higher electric fields. We think that's a way to go. The challenge there is that these cavity fabrications are a lot harder. In principle, throwing platelets onto a surface like an ITF surface would be a lot more tractable, but getting the high field strengths we want, pushing that Rabi frequency up, well above 100 to 200, we're going to require, MEV. We're going to require probably a high electric field, like a dielectric cavity. So Caleb, you have another question. You want a twofer. So you asked about dopant species and dopant distribution. Okay, so we didn't talk about dopants per se. If I assume you mean like doping the platelets, it's an interesting idea, right? This would give Frank and Arkadit some more things to calculate. But there are, so for the general audience, it's well known. There's a well-known history of adding isovalent dopants to cad solenoid nanoparticles like manganese, for example, and you get some interesting photophysics, as well as something our group is looking at, which is alliovalent dopants like silver, or you could add, I guess, copper, either copper plus or copper 2+, and you often get energy states in the band gap. Those can have extremely long lifetimes. Be an interesting question to see about polariton formation with those. That may have been attempted. I have to back my memory, but we haven't done any of that yet with the platelets. Right? So how would the dopant distributions, there's a challenge because just doping platelets is very difficult to get homogeneously, as we've discovered. So if you just took the solution and spun it out, you would get, as it is, in our hands anyway, you would get some platelets that were fully silver selenide, some platelets that were doped, right? And those would have a dopant peak from photoluminescence coming from in the band gap. And then you'd have some undoped platelets that were excitonic emission. So how all of those would couple to the cavity would be, so you'd have to design your cavity probably to be resonant with, let's say, your doped platelets. And then you would have this other reservoir of things that were emitting, in free space, but weren't and it could be significant, right? The exciton emission could be significant, but not coupled to the cavity, at least not to the fundamental mode. So that would be interesting to try. We haven't tried any of that. Okay, and then there's a question on, from Madeline, I guess, on temperature series. So does the absorption cross-section change as a function of temperature? So in the, let me see, in the polariton, that is a good, I'm sorry, in the free space platelet, that's a good question. So I believe it does, I mean, you do get a shift, and there's a well-known shift in the color, right, in the band gap with temperature. And I think you may get a little bit of narrowing, you know, of the peak with temperature, but it's normally in nanoparticles, it's hard to see this in the ensemble because you just have the inhomogeneous distribution swamping everything, right? So you may get, and that's a good question. So you probably would get a slight increase in the oscillator strength, but not much. The Stokes shift of PL and absorption does not, what I remember, does not change with temperature. It tracks pretty well. Not hugely anyway, right? So I hope that answers your question on that. So it does complicate the temperature measurements because so to finish that thought, there's a blue shift in the band gap, right, with temperature. And so you'd have to design your cavity so that when you cooled it or heated it, you didn't go off of resonance, right? And that was an issue. Okay. So there's a question about cavity lifetimes. So I guess if the quality factor is so large, the cavity photon lifetime is really short. Yes, we would agree with that. Why does it matter if the chromophore scientific lifetime is long or shorter? So I guess the question, this goes back to what really is causing the, is causing the lifetime of the polariton, and I don't think it's, at this point, we understand completely what's going into that. I skipped over the data, but we measure lifetimes from the platelets. We've taken a few cuts at lifetimes from polaritons. They don't seem a whole heck of a lot different, but that may be just because you have this massive amount of dark states, right? All of these dark platelets that are coupled. And so if there's coupling, especially via the phonons between all of the upper or lower polaritons and the dark states, then it's possible you're just seeing the longest lifetime there, which is the dark state. But that's a question for to be determined. So it's a good question. I don't have a great answer for you. I hope you hope to be figuring that out. If we could isolate the polariton part or not, right? What is that lifetime? It's a good question. We don't see any real evidence of something that's ultra short, although our current resolution is 10 picoseconds. So, like your calculation would suggest, we would need to go to ultra fast spectroscopy and do a different experiment, for example, an up conversion or something, or a Kerr effect, if we really wanted to see a lifetime that was on the order of a picosecond. We can't quite get there with the photoluminescence straight up. Okay, I think is the last question. Does the polariton remain detectable at room temperature? We detect a Rabi splitting at room temperature. And so I would say, yeah, we do see strong coupling of evidence at room temperature, right? And so the answer would be, yeah, they're detectable. It would be easier, I think, if we had a stronger Rabi splitting, but we do see evidence of it. And then there's a technique question on the software. So, as the sort of PI, I don't do any work, right? So grad students know this, so if you would to send me a note, I could put you in touch with Arkajit or Lang Yu who did the figures on there. Probably Lang Yu is the one who did the cavities, actual color plots, the contour plots. Thanks everybody for the questions. I appreciate it.
Right. So thank you so much for answering all those questions, Professor. Would you be willing to answer one more question from the audience? Who's raising their hand right now?
Yeah.
Okay, thank you. So
we'll give it a shot.
All right.
Hi, Professor. I had a question about your photoluminescence spectra. So I think you might have answered this before, but I don't fully understand why you see photoluminescence mostly only for large incident angle. And you also showed for different detunings, you saw some more photoluminescence from the lower polariton.
Yeah, so let me see if I can get back to that. So I believe the way you could explain that is through probably easiest through the spaghetti plots, right? I mean, so there. So at low angle, you're out of resonance, right? And so even though you see the lower polariton has the photonic character, but it's just not coupling efficiently right to the upper polariton branch of the dark state. When you're in resonant, now you're coupling more strongly, and the photoluminescence then goes from and this is actually a question on the dynamics, and we're thinking about this, right? But so the way that the model is set up is the excitation goes from the hot exciton directly into the dark state, and then couples, right? Then it couples to the lower polariton branch, and we see the emission there.
Okay.
And so if you look at the bottom as well, there's just not a lot of population there in that upper polariton state. It's all in the lower one.
Yeah, so at theta equals 0, you don't see much photoluminescence from the lower polariton branch because it's mostly photonic in nature.
Yeah, we don't see luminescence, period. It's all excitonic at that point.
Okay. Okay, thank you.
All right, so we have just one more question. So we're already almost 10 after, so we're just gonna allow one more question. So Joel, you may talk.
Thank you, Todd. That was a very nice talk. I have a question concerning the PL. So just like with Matt Sphere's paper, do you see that the PL lifetime through the cavity has the same kinetics as outside of the cavity?
Yeah, so that's a good question. I'm not going to say too much on that because we just have some preliminary measurements. There's been a challenge, right? As you start to move to more complicated experiments, applications essentially, then you need more reproducible cavities, right? And so it's been a little challenging to get something with a uniform coupling strength over the whole let's say spot size, right? So as you move your spot around, you don't want to change coupling strength. But that said, it looks like the polariton initial measurements, the polariton lifetime is quite similar to the nanoplatelet lifetime. Yes. However, we don't see any. We're not sensitive yet to, like I said before, to that really short time component, right? We're limited to 10 picoseconds or so on the short time.
Okay, so given that presumably unmodified PL kinetics as outside of the cavity, so I guess there is some well, in the community there is a subset of people who believe that because everything is going to be dominated by the dark state. So here is the question. So if you believe that electron transfer can be modified by the cavity, so then you need to fight against cavity leakage and transfer to the dark states that presumably have the same kinetics as outside of the cavity. So then can you remind me what is the time scale of the electron transfer that you're trying to achieve inside of the cavity?
Yeah, so if we were to use just our catalysts, right, which are quite quick electron transfer, there's two time constants. So let me show you the data. There's a short time constant that's on the order of 20 picoseconds, and then a longer time constant that's on the order of 100 or something. They time average to about 70, but it's a bi-exponential, and that's so. I mean, you could say, okay, the one of the significant charge transfer events is sub 30 picoseconds.
Okay, wait. So then, in that case, that's way longer than the cavity leakage. So then, the only hope to do this is through the dark states.
Yeah.
Okay, but then the big question there is whether the dark states really have a different behavior than outside of the cavity excited states, right? So
yes.
Okay, sounds good. Thank you.
No, I mean, you hit it right on the head. I mean, this is what we're excited to go after. I mean, we fully admit it could fail spectacularly.
Well, no, I mean, I think there are still a lot of questions that haven't been answered. So yeah, I would be very interested to see what happens. Thank you very much.
Yeah, sure. We hope to learn something over the next year to help. But yes, we agree 100% well with what you said.
Great, thank you.
All right, so that's the final question. So thank you so much, Professor, again, for a wonderful talk.
Thank you.
Now, before we finish, I'd like to make a final announcement. All right, so next week, we'll have Professor Pavlos Lagoudakis talking about liquid light computing, room temperature, full logic with Polaritons. So thank you so much, everyone, for attending, and have a great rest of the week. Bye.